Welcome everyone. Today we're going to be talking about data analytics. Specifically, we're going to be taking a trip through machine learning in the form of a couple things. Now, over the course of this series, we're going to be talking about what is machine learning, why do we use machine learning, some examples of machine learning applications, testing and validating, main challenges of machine learning, and types of those systems. So, where does machine learning start and where does it end? What exactly does it mean for a machine to actually learn something? So, if we download, for example, all of Wikipedia to our laptop, did it really learn anything? Is it actually smarter? In this lecture, we're going to really go over and clarify what machine learning is and why we want to use it. Then, before we set out to explore the main machine learning examples itself, we'll take a look at what we want to learn in the main regions of the main landmarks, let's say, of machine learning processes, such as supervised and unsupervised learning, online versus batch learning, instance-based versus model-based learning. Then we will look at the workflow of a typical machine learning project if we have time. And we'll also go through the main challenges that we may face and cover, again, how to evaluate and fine-tune machine learning systems. Now, this presentation is going to basically introduce a lot of the fundamental concepts that every data scientist and decision learning manager should know. So we'll basically do a very high-level overview, and it's going to be relatively simple. And we're going to make sure that everything is crystal clear before we continue on with some of our other more complicated series. So, what is machine learning? Machine learning is the science and art of programming computers so that they can learn from data. So, why do we want to use machine learning? Well, using traditional techniques, we'll need to keep writing new rules forever. So these are such as like using just if, else statements, do loops, while loops, those types of things, in order to create some quote-unquote learning machines. Now, machine learning techniques automatically learn though, okay? So this means that a program is going to be much shorter, and it's going to be much easier to maintain, and it's going to probably and hopefully be more accurate. Now, an area where machine learning shines is for problems that are either too complex for traditional approaches or have no known algorithm. Machine learning can also help humans learn what we do and do not know. Machine learning algorithms can be inspected and seen, what they have learned, at least for some algorithms. Some algorithms can be quite difficult to understand what's going on in the background. Those are those so-called black box methods. Now, problems for which existing solutions require a lot of fine-tuning or a long list of rules, one machine learning algorithm can often simplify code and perform better than a traditional approach. Complex problems for which using a traditional approach yields no good solution, so the best machine learning technique can perhaps find a solution. We also have fluctuating environments. A machine learning system can adapt to new data. Now, getting insights about complex problems and large amounts of data. Again, this is something that was before machine learning was considered almost impossible. So some examples of some machine learning applications. One is analyzing images of products on a production line to automatically classify them. So this is considered image classification. This is typically performed using something like a convolutional neural network. We also detect tumors in brain scans. And this is semantic segmentation, which is going to use something like a pixelated image to classify some type. So for example, what shape of a tumor is or the exact location. And again, this is typically going to be using, again, our convolutional neural networks as well. Automatically classifying news articles. This is natural language processing, and more specifically, text classification, which can be tackled using recurrent neural networks, convolutional neural networks, or transformers. Automatically flagging offensive comments on discussion of forums. This is also a text classification and can be used using natural language processing tools. Summarizing long documents automatically. This is a branch of natural language processing called summarization. And again, it's going to be using the same tools as we talked about above. Creating a chat bot or a personal assistant. Again, this is going to involve natural language processing components as well as natural language understanding, or NLU, to answer questioning and answering modules. Furthermore, some other applications that we have is forecasting your company's revenue for the next year based on performance metrics. Now, this is definitely a regression task and a prediction task that may be used and tackled using a regression model such as a linear regression, polynomial regression model, a support vector machine, a random forest regression model, and even in artificial neural networks. Now, if you want to take sequences into account and of past performance metrics, we may also want to look at recurrent neural networks and convolutional neural networks or transformers. Now, making an app react to voice commands. So this is speech recognition, which requires processing audio file samples. Now they're often too long and they're very long sequences. So they're typically processed using recurrent neural networks or convolutional neural networks or transformers. Detecting credit card fraud is anomaly detection. Segmenting clients based on their purchases so that you can design a different market strategy for each segment. This is clustering. Representing a complex, high-dimensional data set in a clear and insightful diagram. This is data visualization, often revolving around dimensionality reduction. Recommending a product that a client may be interested in based on past purchases. This is a recommender system. One approach is to feed past purchases to an artificial neural network and to get the output the most likely next purchase. This neural net would typically be trained on past sequences of purchases across all clients, building an intelligent bot for a game. So this is often used and tackled by reinforcement learning, which is a branch of machine learning that trains agents or bots to pick up actions that will maximize their rewards over time. Within a given environment, again, this is such as the game. Now, some of the most famous that we know of is AlphaGo, and this was a great example to beat the world champion at the game of Go using reinforcement learning. In the next section, we're going to be talking about types of machine learning. Types of machine learning. There are so many different types of machine learning systems that it's going to be useful to classify them into a broad range of categories. So based on the following criteria: whether or not they are trained with human supervision. This is either supervised, unsupervised, semi-supervised, or reinforcement learning. Whether or not they can learn incrementally on the fly, online versus batch learning. Whether they can simply do something by comparing data points to known data points, or instead by detecting patterns in training data and building a predictive model, such as scientists do. This is instant-based or model-based learning. Supervised and unsupervised learning. Supervised learning. This sort of task is again going to be usually called something like a regression, and we're going to use it to train systems on many different types of examples, such as cars. This is going to be including their predictors and their labels, ergo to predict their prices. Now, in supervised learning, the training set you feed to the algorithm includes the desired solutions. These are called the labels. A typical supervised learning task is classification. Another typical task is to predict the target value, such as the price of a car, given a set of features called predictors. This sort of task is called regression. To train the system, you need to give it many examples of cars, including both their predictors and their labels, also their prices. So here we can see that there's an example of a classification of a labeled training set for spam classification. As you can see in the example here, we have, let me grab this. So here, for example, we have labeled data, okay, some instances here. And then we have non-labeled. So again, we don't know exactly what these are. So these are, let's say that these are good, these are bad. So for example, this is not spam, this is a correct email, and this is spam. Now we can use all of this training set of data in order to make a prediction on some new email that we're receiving, whether this is going to be a spam email or whether it's a correct email or a ham email. Here we have another example of a regression. Now this regression problem itself is going to be used to help predict some given value. So some given value here would be, maybe we have some new instance that's going to be at this point here. And so then we can go and we'll basically follow all the way up to the closest value here. And it should, again, our estimate would be, it would be somewhere along this line here, given some value. Now again, maybe we have some multiple input features and again, multiple output values. And so that's going to allow us to have a better prediction of our model. And again, we've seen this in a couple different examples in the past. Again, almost everyone has seen some sort of regression problem, such as this. The most common types of supervised learning algorithms are k-mean, nearest neighbors, linear regression, logistic regression, support vector machines or SVMs, decision trees, random forests, and neural networks. Unsupervised learning. And unsupervised learning, as we might have guessed, is the training data is unlabeled, and the system tries to learn without a teacher. So here we can see an example of some unlabeled data. Now, if we were using a type of some sort of machine learning algorithm, okay, maybe it would give us maybe two sets this way, okay? Or maybe it would break it into 3, maybe it would group it into 4, okay? And again, this is just going to depend on what type of algorithm and what data you're feeding into it. So the most common types of unsupervised learning algorithms are clustering, and this is from k-means, a DB scan, or hierarchical cluster analysis. We also have anomaly detection and novelty detection, and so one is something like one-class SVMs or isolation forest. The most common unsupervised learning algorithms, again, as we have is some visualized and dimensionality reduction. So these are principal component analysis, or PCA. We have kernel principal component analysis, locally linear embedding, or LLE, and T-distributed stochastic neighbor embedding, or TSEN, or SNE, sorry. Associated rule learning, which is a priori, or LCOT, or LCLOT. And then here we see our example of our clustering algorithm that we saw before with the answers. Now let's say that we have a bunch of data to maybe to our company's website. Okay. Now you want to run a clustering algorithm to try and detect which groups of visitors are similar to one another. So this is what you would see here in our figure. Now, at no point do we tell the algorithm which group our visitors belong to. It finds those connections without our help. So for example, it might notice that, let's say, 40% of your visitors are female who like computer science and they generally visit your website in the evening, okay? Now, while 20% of yours are male and they like to visit your data set on the weekends. Now, if you use hierarchical clustering algorithm, it may also subdivide the group into smaller subgroups, and this may help you target your audience by their group. So this visualization here is, again, this is a TSNE, And again, it's going to be great for semantic clusterings. So visualization algorithms are also going to be good examples of unsupervised learning algorithms. Now, we're going to feed them a lot of complex and unlabeled data, and they output either a 2D or 3D representation of our data. Now, these algorithms try their best to preserve as much of the structure as they can. Again, trying to keep separate clusters in the input space from overlapping with the visualization, so that you can understand how the data is organized and perhaps identify unsuspected patterns. Now, a related task is dimensionality reduction, now in which the goal is to simplify the data without losing too much information. One way to do this is to merge several correlated features into one. For example, let's say a plane's mileage may be strongly correlated to the age of the plane, so that the dimensionality reduction algorithm will merge them together into one feature that represents the plane's wear and tear. This is called feature extraction. So here we have an example of an anomaly detection algorithm. So this is also a very important unsupervised learning task. So for example, if we're wanting to detect unusual credit card transactions and prevent fraud, okay, we're going to be catching, maybe we also want to catch manufacturing defects or automatically removing outliers from our data sets before feeding it to another learning algorithm. The system is shown mostly normal instances during training, so it will recognize them. Then, when it sees a new instance, it can tell whether it looks like a normal one or whether it looks like an anomaly, or it's most likely an anomaly. A very similar task is novelty detection. It aims to detect new instances that look different from all the instances in the training set. This requires having a very, very clean training set, devoid of any instances that would like the detection of the algorithm. So again, we don't want any mistakes in that data. So for example, if you have a picture of thousands of cats and 1% of those maybe are like earless cats or something like that, okay? Or short-tailed cats, then the novelty detection algorithm should now treat new pictures such as of those short-tailed cats or no-eared cats as novelties. On the other hand, anomaly detection algorithms may consider these cats as so rare, so different from other cats that you would most likely classify them as anomalies. Okay, so again, this is all something that we need to always be aware of whenever we're asking for clean data and what we're training our data for. Semi-supervised learning again is learning with something like two classes, as we can see here. We have our triangle class here, and we have our square classes over here. But then if we have another class over here, again, which one does this technically belong to? Is it going to be a square, or is it going to be a triangle? Okay, so since labeling the data is usually very time-consuming and costly, we'll often have plenty of unlabeled instances and a few labeled instances. Some algorithms can deal with data that is partially labeled. This is called a semi-supervised learning. So some photo hosting services are a very good example of this. Once you upload all of your photos to a service, it's going to automatically recognize maybe people, okay? And it's going to show, and the person, for example, maybe shows up in photos 1, 10, and 25, while another person shows up in 2, 6, and 13. Now, this is an unsupervised part of the algorithm, or clustering. Now, that the system needs is for you to tell it who these people are. Just add one label per person and is able to name everyone in the photo, which is very useful for searching for photos. Most semi-supervised learning algorithms are combinations of unsupervised and supervised learning algorithms. For example, deep belief networks, or DBNs, are based on unsupervised components called restricted Boltzmann machines, or RBMs, stacked on top of one another. RBMs are trained sequentially in an unsupervised manner, and then the whole system is fine-tuned using supervised learning techniques. Reinforcement learning is a very different beast altogether. The machine learning system, called an agent, is in this context, can observe the environment, select and perform actions, and and get rewards in return. So the machine learning system, called an agent in this context, can observe the environment, and it can select and perform actions and get rewards in return, or penalties in the form of negative rewards. It must then learn by itself what is the best strategy, called a policy, to get the most reward over time. A policy defines the action the agent should choose when it is given a situation. For example, many robots implement reinforcement learning algorithms to learn how to walk. Same with the AlphaGo program is a good example of reinforcement learning. It made headlines in May of 2017 when it beat the world champion Ke Jie at the game of Go, and learning its winning policy by analyzing millions of games and then playing many games against itself. Note that the learning was turned off during the games against the champion. AlphaGo was just applying a policy that it had learned. Batch and online learning. Another criterion used to classify machine learning systems is whether or not the system can learn incrementally from a stream of incoming data. Batch learning. In batch learning, the system is capable of learning incrementally. It must be trained using all the available data. Generally, it takes a lot of time and computing resources, so it can typically be done offline. First, the system is trained, and then it is launched into production and runs without learning anymore. It just applies what it has learned. This is called offline learning. If you want a batch learning system to know about new data, such as a new form of spam data or spam emails, you need to train a new version of the system from scratch on a full data set, not just the new data, but also the old data. Then stop the old system and replace it with a new one. Fortunately, the whole process of training and evaluating and launching a machine learning system can be automated fairly easily. So even a batch learning system can adapt to change. Simply update the data and train a new version of the system from scratch as often as needed. This solution is simple and often works fine, but training using the full set of data can take many hours, so you would typically train a new system only every 24 hours or even just weekly. If your system needs to adapt to rapidly changing data, ergo predicting stock market prices, then you should need a more reactive solution. Also, training a data on a full set of data requires a lot of computing resources: CPU, memory space, disk space, etc. If you have a lot of data and you automate your system to train from scratch every day, it will end up costing you a lot of money. If the amount of data is huge, it may even be possible to use a batch learning algorithm. Finally, if your system needs to be able to learn autonomously and it has limited resources, such as a smartphone application or even, for example, a Mars rover or moon lander, then carrying around large amounts of training data and taking up a lot of resources to train for hours every day is a showstopper. Fortunately, a better option in all of these cases is to use algorithms that are capable of learning incrementally. Online learning. In online learning, you train a system incrementally by feeding it data instances sequentially, either individually or in small groups called mini batches. Each learning step is fast and cheap, so the system can learn about new data on the fly as it arrives. Online learning is great for systems that receive data as a continuous flow, such as stock prices. and need to adapt to change rapidly or autonomously. It is also a good option if you have limited computing resources. Once an online learning system has learned about new data instances, it does not need them anymore. So you can discard them unless you want to be able to roll back to the previous state and replay the data. I would highly recommend this. This is a huge, this can save a huge amount of space. So as we can see from the plot we have here, okay, we have some sort of data here, and again, this would be like the full streaming data. We train our machine learning algorithm, and then we want to evaluate the system. Now, if it is good, we move forward with launch. If it evaluates bad, then we start training the algorithm all the way over again and start at the beginning. Again, once we launched and we run and learn, again, it's going to take in this new data on the fly, and it's going to be making those predictions as you go along. So, online learning and huge data. Now, online learning can also be used to train systems on very large amounts of data or huge data sets that cannot fit in a machine's main memory. This is called out-of-core learning. Out-of-core learning is usually done offline, i.e., not on a live system. So online learning can be a confusing name. Think of it as incrementally learning or incremental learning. The algorithm loads a part of the data, runs a training step on the data, and repeats the process until it has run on all of the data. One important parameter of online learning systems is how fast they should adapt to changing data. This is called the learning rate. If you set a high learning rate, then your system will rapidly adapt to new data. But it will also tend to quickly forget the old data. You don't want a spam filter to flag only the latest kinds of spam it is shown. Conversely, if you set a low learning rate, the system will have more inertia. That is, it will learn more slowly, but it will also be less sensitive to noise in the new data or to sequences of non-representative data points, such as outliers. A large challenge with online learning is that if bad data or corrupt data is fed into the system's performance is going to gradually decline. So again, the adage is garbage in, garbage out. If it's a live system, your clients will definitely notice. So for example, if corrupt data or bad data could come from a malfunctioning system or a sensor of a robot, or from someone spamming a search engine to try and rank high in the search results, to reduce this risk, you need to monitor your system very closely and promptly switch learning off, and possibly even revert back to a previous instance. If you detect a drop in performance, you may also want to monitor the input data and react to abnormal data. So again, maybe adding in an anomaly detection or outlier detection algorithm to take care of that. So as we see with our visual here, we have a lot of data. Now if we chop this into many batches, okay, then we can train our online learning system. We do the same evaluation. If it's good, we launch it. If it's bad, we need to add in this extra step here and analyze in what type of errors are happening. Okay, and then we need to study those errors to see what that problem actually is. Because again, maybe it's a faulty sensor. Maybe we have some outliers that keep popping up in our data set. We don't know exactly what's going on, so we need to make sure that we can really study out that problem. And once that's done and we've updated our algorithm, we can train our online algorithm once more and start the process over again. Again, you can see that this may take several iterations for everything to work out the way that you want. Next up, we have instance-based versus model-based learning. One more way that we categorize machine learning systems is by how they generalize. Most machine learning tasks are about making predictions. This means that given a number of training examples, the system needs to be able to make good predictions in order to generalize to some examples it has never seen before. Having a good performance measure on a training data is good, but insufficient. The true goal is to perform well on new instances, and the two main approaches to generalization is instance-based learning and model-based learning. Instance-based learning is the system that learns by examples, the examples by heart, then generalizes to new cases by using a similarity measure to compare them to the learned examples. Now, possibly, the most trivial form of learning is simply to learn by heart. If you were to create a spam filter this way, it would just flag all emails that are identical to emails that have already been flagged by users. Not the worst solution, but certainly not the best. Instead of just flagging emails that are identical to known spam emails, your spam filter could be programmed to also flag emails that are very similar to known spam emails. This requires a measure of similarity between the two emails, and a very basic similarity measure between two emails could be the count of words that they have in common, and the system would flag an email as spam if it has many words in common with a known spam email. So as we see with this graph that we have here, we can see, for example, we have this new instance, and again, we have all of our training instances, and maybe here it's checking out what is nearest to it. So for example, in this instance, it only has one box, but it has two triangles. Okay, well, in this type of learning algorithm, then we would probably say that this new instance is most likely a triangle. Model-based learning is to generalize from a set of examples to build a model of these examples and then use that model to make predictions. So as we can see with this particular example, we've used a model to train the data set, and we can see that it has kind of sectioned off the data, almost like a clustering algorithm here. And it says, all right, anything that falls to the left of this line and above this line area here is going to be considered a triangle. Everything outside of it is going to be a square. Again, these are quite simplified examples, but it still works for our case. So another model-based learning example is something very similar to some economic models, such as looking at life satisfaction and GDP per capita. So for example, suppose we want to know if money makes people happy. So we can look at the Better Life Index from the OECD website and look at the stats of gross domestic product per capita from the IMF website, and then we can join the two tables and sort by GDP per capita. Now, there does seem to be a trend here. Though it is pretty noisy in the data, it also looks like the satisfaction goes up more or less linearly. So, and again, that's with respect to satisfaction goes up with respect to an increase in GDP per capita. So we could decide that the model life satisfaction is a linear function of GDP per capita. This step is called model selection. You selected a linear model of life satisfaction with just one attribute, GDP per capita. So how can we know which values will make your model perform best? To answer this question, you need to specify a performance measure. You can either define a utility function or a fitness function that measures how good your model is, or you can define a cost function that measures how bad it is. For linear regression problems, people typically use a cost function that measures the distance between the linear model's predictions and the training examples, and the objective is to minimize this distance. This is where the linear model algorithm comes in. You feed it in training examples, and it finds the parameters that make the linear model fit best to your data. This is called a training model. So as we can see with this example, we have several different training models. So let's start, we'll go from the bottom to the top. So this first model is where theta naught is equal to 0. So we would have maybe something like y is equal to theta naught plus theta 1 of x. well, that's a theta, plus, and then some error term maybe. So we see here that if theta is 0, and then our model is something like 2 multiplied by 10 to the negative fifth, again, we see that it's definitely not going to be representing our data. Maybe the angle is almost correct, but it's definitely not representative of our data. Now, let's go up to this one as well. So here, if our theta naught is 8, and again, that's our intercept here, and we check and it's negative 5, so the slope is negative in this instance, then this is definitely not going to be the case, because we already know that, at least looking at the data, that we have a positive trend with our data. Finally, we have this theta naught is equal to 4, and our theta 1 is equal to 5 multiplied by 10 to the negative fifth. Well, this is definitely getting closer to what we want, but I would still say that maybe we're in the ballpark, but we're not in the best model that we could be. So here, let's actually take a look at a further example and maybe a little bit more of a perfection of the model. We can finally be ready to run our model and make our predictions. So for example, say that you want to know what people from Cyprus are happy or not. And the OECD data does not have an answer. Fortunately, you can use your model to make a good prediction. You can look up Cyprus's GDP per capita, and then you find that $22,587 is what it is per capita, and then apply that to our model, and we can find that the life satisfaction is theta naught is going to equal 4.85, and our theta 1 is going to be 4.91 times 10 to the negative fifth. And notice here that this is definitely a better fit than we had before. Okay, so again, we notice that somewhere along the line, our Cyprus knots are going to fit along that line. Next up, we'll be talking about the main challenges of machine learning. The main challenges of machine learning. Since your main task is to select a learning algorithm and train it on some data, the two things that can go wrong are bad algorithm and bad data. Insufficient quantity of training data. It takes a lot of data for most machine learning algorithms to work properly. Even for very simple problems, you typically need thousands of examples. And for complex problems such as image or speech recognition, you need millions of examples, unless you can reuse parts of an existing model. Non-representative training data. Sampling noise. If the sample is too small, i.e., the non-representative data as a result of chance. Sampling bias. Even very large samples can be non-representative if the sampling method is flawed. In order to generalize well, it is crucial that your training data be representative of the new cases you want to generalize to. This is true whether you use inference-based learning or model-based learning. By using non-representative training data, we've trained a model that is unlikely to make accurate predictions, especially for very poor and very rich countries. It is crucial to use a training set that is representative of the cases you want to generalize to. This is often harder than it sounds. Poor quality data. If your training data is full of errors, outliers, and noise due to poor quality measurements, it will make it harder for the system to detect the underlying patterns, so your system is less likely to perform well. It is often well worth the effort to spend time cleaning up your training data. The truth is, most data scientists spend a significant part of their time doing just that. Irrelevant features. Feature engineering is a critical part of the success of a machine learning project, is coming up with a good set of features to train on. Feature selection is the selecting the most useful features to train on among existing features. Feature extraction is combining existing features to produce a more useful one, ergo dimensionality reduction algorithms. Feature creation is creating a new features by gathering new data. Overfitting the training data. Overfitting means that the model performs well on the training data, but it does not generalize well. Overgeneralizing is something that we humans do all too often, and unfortunately, machines can fall into the same trap if we do not be careful. So what we can see with this example here is definitely a classic case of overfitting. This first section here seems to be relatively well generalized, but if you notice here, there are definitely some spots that seem to almost be too good. Again, if you see a model, and again, like here, if these models seem to be too good, okay, particularly if you're just visualizing the model, then they probably are. Why does overfitting happen, and how do we correct it? Overfitting happens when the model is too complex relative to the amount and noisiness of the training data. There are some possible solutions. 1. Simplify the model by selecting one with fewer parameters, ergo a linear model rather than a high-degree polynomial model, by reducing the number of attributes in the training data or by constraining the model. 2. Gather more training data. 3. Reduce the noise in the training data, ergo fix data errors and remove outliers. Regularization, constraining a model to make it simpler and reduce the risk of overfitting. So as we can see here with our model that we've been looking at, there are several different examples that we have. So we have here 3 separate types, okay? So we have a linear model on all the data, we have a linear model on partial data, and then we have a regularized linear model on partial data. So as you can see, there is a definite variation between these their outcomes. They even have a tendency to crisscross on one another. So whether one model is better or not, again, you can see that this regularized model has a tendency to be between both of the other 2 models, so it's probably the most generalizable of the 3 models. Next, we have hyperparameters. So a hyperparameter is the amount of regularization to apply during learning can be controlled. A hyperparameter is a parameter of a learning algorithm, not the model. As such, it is not affected by the learning algorithm itself. It must be set prior to training and remains constant during training. If you set the regularization hyperparameter to a very large value, you will get an almost flat model. Ergo, the slope is 0. The learning algorithm will also certainly not overfit the training data, but it will be less likely to find a good solution. Tuning hyperparameters is an important part of building a machine learning system. Underfitting the training data. Underfitting is the opposite of overfitting. It occurs when your model is too simple to learn the underlying structure of the data. So how do we correct underfitting? 1. Select a more powerful model with more parameters. 2. Feed better features to the learning algorithm with feature engineering. 3. Reduce constraints on the model, ergo reduce the regularization hyperparameter. So now let's do a quick review. Now let's take a quick review of what we've covered so far. Machine learning definition. Machine learning is about making machines get better at some tasks by learning from the data instead of having it explicitly code rules. There are many different types of machine learning systems: supervised or unsupervised, batch or online, instance-based or model-based. Machine learning projects. In a machine learning project, you gather data in the training set and you feed that training set to a learning algorithm. If the algorithm is model-based, it tunes some parameters to fit the model to the training set, i.e. to make good predictions on a training set itself, and then hopefully it will be able to make good predictions on new cases as well. If the algorithm is instance-based. It just learns the examples by heart and generalizes to new instances by using a similarity measure to compare them to the learned instances. Machine learning systems. The system will not perform well if your training set is too small, or if the dataset is not representative, is noisy, or is polluted with irrelevant features. Your model needs to be neither too simple nor too complex. The system will not perform well if your training set is too small or it's not representative. Your model needs to be okay, let me stop there. Testing and validating data. We split our data sets into two sets. We usually follow the 80-20 rule. It is common to use 80% of the data for training and hold out 20% of the data for testing. However, this depends on the size of the dataset. If it contains 10 million instances, then holding out 1% means your test will contain 100,000 instances, probably more than enough to get a good estimate of a generalization error. Our training set is to train your model using a training set. The test set is to test it using the test set. Generalization error. The error rate on new cases is called the generalization error or out-of-sample error. And by evaluating your model on the test set, you can get an estimate of this error. This value tells us how well your model has done performing on instances it has never seen before. If the training error is low, i.e. your model makes few mistakes on the training data, but the generalization error is high, it means that your model is overfitting the training data. Hyperparameter tuning and model selection. Suppose you are hesitating between two types of models. How can you decide between them? One option is to train both and compare how well they generalize to the test set. Suppose that the linear model generalizes better, but you want to apply some regularization to avoid overfitting. How do you choose the value of the regularization hyperparameter? One option is to train 100 different models using 100 different values for the hyperparameter. Suppose you find the best hyperparameter value that produces a model with the lowest generalization error, say just 5% error. You want this model into production, but unfortunately it does not perform as well as expected and produces 15% errors. What just happened? The problem is that you measured the generalization error multiple times on the test set, and you adopted the model of the hyperparameters to produce the best model for that particular set. This means that the model is unlikely to perform as well on new data. Hyperparameter tuning and model selection. What is the solution? Holdout validation. If you simply hold out part of the training data to evaluate several candidate models and select the best ones. Train multiple models with various hyperparameters on the reduced training set. Select the model that performs best on the validation set. After this holdout validation process, you train the best model on the full training set, and this gives you the final model. Evaluate this final model on the test set to get an estimate of the generalization error. The new holdout set is called the validation set, or sometimes the development set or dev set. Specifically, we train multiple models with various hyperparameters on the reduced training set, i.e. the full training set minus the validation set. Select the model that performs best on the validation set. After this, without validation process, you train the best model on the full training set, including the validation set, and this will give you the final model. Evaluate this model on the test set to get an estimate of the generalization error. Now, there are some potential issues. If the validation set is too small, then the model evaluations will be imprecise. If the validation set is too large, then the remaining training set will be much smaller than the full training set. Why is this bad? Well, since the final model will be trained on the full training set, it is not ideal to compare candidate models trained on a much smaller training set. The best way to solve this problem is to perform repeated cross-validation using many small validation sets. Each model is evaluated once per validation set after is trained on the rest of the data. By averaging out all the evaluations of the model, you get a much more accurate measure of its performance. Data mismatch. In some cases, it's easy to get a large amount of data for training, but this data probably won't be perfectly representative of that data that will be used in production. An example of this is training data in video quality and the actual input quality.